Now that we've talked about some of the background and general information about NMR, we are going to turn our attention to proton NMR spectroscopy. In our preview slide, we talked about the number of signals, chemical shift, integration, and splitting. In this next series of videos, we're going to look at each of these in turn. So in this video, we are going to focus on the number of signals. Now, the number of signals in a proton NMR spectrum gives us information on the number of types of hydrogens, or how many sets of hydrogens do we have. So we are going to focus on equivalent versus non-equivalent hydrogens. If we think about a CH3 group, for example, well, here's a carbon, it's connected to another carbon. This carbon is tetrahedral, so this is what our hydrogens are going to look like. Here's our shape. Well, if we were to take a snapshot, then this hydrogen is in a different environment than this one or this one. But because there is free rotation around this bond, then these are going to move, so that in one instant, this particular hydrogen is up in the plane, and the next instant, maybe it's going to be over here behind the plane, and the next instant, it is in front of the plane. So the rotation is quick enough that the NMR will see them as the same thing. And so they are equivalent to each other. For simple compounds, hydrogens connected to the same carbon are equivalent. In this first example, we have a CH3 group here, and we have a CH3 group here. Okay, the CH3s are the same, but let's think more about the environment. These hydrogens are connected to a carbon that's connected to a carbonyl. These hydrogens are connected to a carbon that's connected to a CH2 group. And so even though they're both CH3s, these hydrogens don't have the same electronic environment. And so this is going to give us different signals. So these hydrogens are not equivalent to these hydrogens. Furthermore, because this is a CH2 group, it's obviously different than a CH3 group. So this is another set of hydrogens. So in this example, we have 3 types of non-equivalent hydrogens, which is going to give us 3 signals on the NMR spectrum. If we look at our next example, we have a CH3 connected to a CH2 connected to a CH3. Well, the CH2 is different from the CH3s, so we know that this is going to give us a signal that is different from the CH3 groups. But if we think about the CH3 groups, there's symmetry in this molecule. And so this CH3 group is exactly the same as this CH3 group. So looking for symmetry, this is a very important feature when we are talking about the number of signals. Now, keep in mind, it doesn't look symmetric based on the way that it's written, but you need to think about the actual shape of the molecule. And so this methyl group is chemically equivalent to this methyl group. And so this is going to give rise to a single signal, which is still distinct from the CH2 group. So we will have one signal from the CH2 group, and then we will have another signal from both CH3 groups. So we get 2 signals total. In our next example, we have this set of hydrogens connected to a regular sp3 hybridized carbon. We have this set of hydrogens. They're not in the same environment as the CH3 group, so it's a distinct signal. And then we also have the hydrogen connected to the oxygen. That is definitely in a different environment, and so it gives a distinct signal. So here we have 3 signals again. Now over here, we want to think about symmetry. It doesn't have to be symmetry that goes right down the molecule. We just want to keep in mind the fact that we have free rotation around some of these bonds, well, around all of these bonds. So for example, well, here we have a CH, and this is the only CH, so that is a unique signal. It's not equivalent to anybody else. Here we have a CH2 group. It is our only CH2 group, so that is also distinct and it gives a separate signal. Now we have two CH3 groups and three more CH3 groups. Well, these CH3 groups are both connected to the same carbon, and then there's free rotation around this carbon-carbon bond, which means this methyl group can rotate and be in the position of this methyl group, and they can keep rotating. And so what that leads to then is that these methyl groups are equivalent to each other. So these two sets of hydrogens really count as one set, giving us one signal. And then over here, we have these CH3 groups. They are not the exact same as these CH3 groups. These CH3 groups are connected to a C that's connected to an H. These CH3 groups are connected to a C that is connected to no H's, and so they are different. But because we have free rotation around this bond, these methyl groups are equivalent to each other. So these are equivalent to each other, but they are different than these, which are different than these and different than these. So that gives us 4 signals in this case. In our next example, we have a ketone and we have symmetry in this molecule. So here is our carbonyl group, and then on either side of the carbonyl group, we have the CH2 groups, and then next to those are CH3 groups. So because of the symmetry, we're going to have one signal from these hydrogens and one signal from these hydrogens, so a total of 2 signals because of the symmetry. On this next one, we have a CH3 group and a CH3 group, and they're on either side of the carbonyl, but they're not exactly the same. They're similar to each other, but they're not equivalent because we do not have symmetry in this molecule. Here we have a CH2, another CH2, and another CH2. This CH2 is definitely different from the others because it's not next to a carbonyl. So this one gives its own signal. Now these two are similar because they're both CH2 groups that are next to a carbonyl. But similar is not the same as equivalent. This CH2 group is next to a carbonyl, but it's also next to a CH3. Whereas this CH2 group is next to a carbonyl, but it's also next to a CH2. So they're not exactly the same, and so they're going to give rise to 2 different signals. And then the CH3 groups, this CH3 is next to a CH2, this CH3 is next to a CH2. But once again, they're not completely identical. This CH3 is next to a CH2 that's next to a carbonyl, whereas this CH3 is next to a CH2 that's next to another CH2. So these groups are not exactly the same, so they're going to give rise to separate signals. So here we're going to have a total of 5 signals. In our next example, we have this hydrogen by itself. The aldehyde hydrogen is distinct from the others, separate from the CH2 group, separate from the CH3 group. We have 3 signals. Next, let's look at some examples with multiple bonds. So in this case, we have a double bond. We have 2 hydrogens connected to the same carbon. Now up here, when we had 2 hydrogens connected to the same carbon, we said that they were equivalent to each other, but that's because we had single bonds and there's free rotation. Here we have a double bond, and keep in mind in terms of the alkene structure, because of that pi bond, there is not rotation around this carbon-carbon bond because that rotation would require breaking the pi bond. So this hydrogen and this hydrogen, although they are connected to the same carbon, they are not equivalent to each other. This hydrogen is close to an alkyl group, whereas this hydrogen is close to another hydrogen. And so these are distinct from each other. So this gives us a signal, this gives us a separate signal, this gives a separate signal. And then we have the CH2 group is a distinct signal, and then the CH3 group is another distinct signal. So we're going to have 5 signals in this molecule. Here we have an alkyne. We have this hydrogen connected to an alkyne carbon, very different from the CH3 group. This gives us 2 signals. Now here we have an aromatic ring connected to a side chain. And if we think about symmetry, then we have symmetry that goes through here. So this CH3 group is different than this CH2 is different than this CH2. This carbon is not connected to any hydrogens. This carbon is connected to a hydrogen, and so is this one. And because of the symmetry, this hydrogen is equivalent to this hydrogen. So these 2 hydrogens will give rise to 1 signal. These 2 hydrogens are the same as each other, but they are just a little bit different than these hydrogens. So this will give another signal. And then finally, the hydrogen on this carbon will give another. So here we are looking at 6 signals. Now, in our last 3 examples, we have a benzene ring with a methyl group and an ethyl group, but they're in different locations relative to each other. Once again, we need to keep thinking about symmetry. In the last molecule, we have symmetry that goes this way. And so these hydrogens on the aromatic ring are equivalent to each other, and these are equivalent to each other. But these hydrogens are not equivalent to these hydrogens, all right? So we will get 2 separate signals. We will also get a signal here, here, and here, so 5 signals. On the first and second example, we don't have symmetry because here we have a methyl compared to an ethyl, so it's not symmetry along here. Therefore, we have this is distinct, this is distinct, this is distinct, and then this is different than this one, is different than this one, is different than this one. This carbon has no hydrogens, this carbon has no hydrogens. So here we have a total of 7 signals. So notice here, because of symmetry, we only had 5. Here we have 7. And then over here, we've got this methyl group different than this methyl group, different than the CH2. This hydrogen is different than this hydrogen, is slightly different than this hydrogen, is different than this hydrogen. So once again, 7 signals. Now, looking at a compound, I want you to be able to identify hydrogens that are equivalent or not equivalent so that you can predict the number of signals. As we look in the other direction, if you look at a spectrum and you're trying to figure out the structure, well, sometimes you need to consider some of the nuances. Even though this gives rise to 7 distinct signals, some of these signals are very, very similar to each other, and so they might overlap. And so you don't always see all of that detail. Sometimes we will be able to identify 4 separate hydrogens in the aromatic region, and we can get that detail. In other cases, we're just going to focus on how many hydrogens are there. So looking at the compound, you should predict the number of signals. But looking at the spectrum, you need to be a little bit flexible in your interpretation of how many signals there actually are, because of the fact that different signals that are similar to each other can overlap, which makes it a little bit harder to distinguish. So with this set of compounds, we've looked at a number of examples where there is symmetry, where there is not symmetry, and we need to think about the different environment, which leads to different types of hydrogens, which leads to different signals.